Next, we know that voltage equals E times the distance, which comes from the circular integral of E dot ds. And if E is in the direction of the path S everywhere, this is just E times the length of the E path. And we'll be using that later. Next, we know that flux E is the circular integral of E dot dA. And if E is in the direction of the normal to A everywhere, this is just E times the E area. We'll be using that soon. We also know the circular integral of B dot ds is Z here. And if we were to integrate, well, we take B times the length of a path, which is in the direction of B everywhere, we end up with B times B path. We'll be using that soon. Now we know the circular integral of B dot dA is flux B, and similarly that can be written as B times the area of B. At this point, I think we're ready to start identifying these lines. Starting here, you know, going from, well, E times the path gives us V, so we'll label this as E path as we go this way. And this gives us, well, then we'll come down here. See, B times B path gives us Z. So this is B path going this way. Now we know that this flux E over E is an area, so this must be E area over E path. And now we see that if we cross three lines, we're talking about some sort of a volume. And if any three consecutive lines, we should be talking about the same volume. So that means that we should be repeating this pattern down here. This is E area over E path, going in that direction. And this would be E path in that direction. And down here you end up with B path going in that direction. And it's important to know that it's always the same volume, whatever three lines you're crossing. And that volume, if we look at it, is B path times E path times E area over E path. So volume is E area over E path times E path times B path. And this is the volume that we're talking about. We can see that this is E area times B path. And in some cases that is a readily apparent physical volume, and sometimes it is not. But this is the volume which is constant in any three lines you cross. So now we will fill in the rest of our boxes using our pattern, mu q. This would be mu q times E path. And this would be mu q times E area, multiply by E area over E path. This one up here, this line again is B path. So this is mu naught Q, E area, B path, or mu Q times volume. If we go down here, this is mu naught Q over B path, mu naught Q over B path, E path over E area. Down here, we go mu naught Q B path, E area, which is just mu Q over volume. And we can follow the same pattern in next column here. This is mu naught I path, mu naught I area, and this is mu naught I E area B path, which is mu naught I volume. And we can also go on down here. This is mu naught I over B path, mu naught I over B path, E path over E area, mu naught I over volume. And then this would be mu naught I over B path, 1 over volume. This is the volumetric density of B. Come on, into this column, this becomes mu naught I B path. Gets really monotonous. It's Q over epsilon, but it's also mu naught. This better be a di dt here. Di dt E area. And this would be mu naught di dt times our volume, E area times B path. And we can go ahead and fill in the rest of the boxes, but that gets pretty boring. I think we will skip that detail for the moment.